Welcome to the deep dive. Today, we're plunging into a stack of sources that take us way beyond just the formulas of physics. We're looking at the deep philosophical shifts Isaac Newton brought about.
That's right. We've got material here showing how Newton didn't just, give us laws for how things move or fall.
Yeah.
He fundamentally re-architected our whole understanding of the universe's bedrock: space, time, motion, reality itself.
Absolutely. So our mission for this deep dive is to unpack how Newton built on and really pushed back against centuries of thinking, from Aristotle all the way through Descartes to create this picture of the world that, well, it dominated physics for 200 years.
Yeah, we're digging into the philosophical foundations that made classical physics even possible.
It sounded like quite the intellectual battleground.
Oh, it was. Get ready for a journey into the 17th century where science and philosophy were just completely intertwined. How Newton tackled these dot questions and the new questions his answers raised really set the stage for everything that followed.
Okay, let's unpack this. Where did the sources say the synthesis even began? What was the absolute core of it?
Well, the core, as these sources presented, was providing a single, unified framework. This was huge.
Unified how?
For millennia, people thought the rules for stuff on Earth, like, falling apples, were totally different from the rules for the heavens orbiting planets and stars. Newton came along and said, nope, same laws apply everywhere.
So the falling apple and the orbiting moon aren't just neat stories. They're literal examples of the same underlying physics.
Exactly. This unified view just abolished that ancient split between the heavens and the Earth. And beyond that, his synthesis moved physics from just describing how things move, Kepler's ellipses, Galileo's parabolas.
You're really describing patterns.
Yes, to actually explaining why they move that way.
Okay, an explanation based on what then?
Based on underlying forces and precise mathematical laws. This was revolutionary. It basically established the idea of the universe as this vast mathematical machine, something we could understand through reason and calculation.
So less mystery, more mechanics?
In a way, yes. And the sources really emphasized this wasn't just science changing, it was philosophy changing. Redefining space, time, motion, cause and effect, laying the groundwork for what we now call classical physics. It definitely grew out of that mechanistic worldview, influenced by Descartes and others, but Newton took it somewhere very different.
Speaking of roots, the sources point to something, well, surprisingly simple as a starting point for Newton's thinking about forces. Just collisions. Simple impacts.
It's fascinating, isn't it? He started by looking really closely at simple impacts, like particles hitting each other. And he noticed two key things. First, before they hit, the particles just seemed to move in perfectly straight lines at a constant speed.
Okay, uniform motion.
Right. And second, at the very instant of impact, there was a sudden, really abrupt change in their motion.
Sudden, not like a gradual push.
No, the sources suggest his initial idea of a motive force was tied to this instantaneous change. Force was something acting right at the collision moment, causing an immediate exchange or redirection of motion. Think of momentum being instantly rerouted, not continuously altered.
Huh. And these simple observations, the straight line motion before and the sudden change at impact, somehow grew into his three laws.
That's the argument presented here. You can trace the lineage. The first law objects keep their state of motion unless a force acts seems to come straight from that observation of uniform motion before impact.
Makes sense. Inertia.
Exactly. The second law force causing a change in motion or momentum is rooted in that sudden change at the moment of impact, driven by that motive force.
Right. Femma, essentially, though, maybe not formulated quite like that yet.
Well, more like force is proportional to the change in momentum. And the third law, action and reaction, are equal and opposite that comes from the exchange of motion during the collision. The fact that the momentum seemed conserved in these interactions.
Okay, so the core idea of force causing a change in motion came from looking at things bumping into each other. But his laws famously apply to smooth, continuous motion too, like planets orbiting. How did he bridge that gap from sudden impacts to continuous forces?
That's the next crucial step. The sources highlight his analysis of curved motion, like an object swinging in a circle. He built on work by people like Huygens, who'd figured out the math for centrifugal force, the outward pull. Newton took that and applied his own developing idea of inertia.
Which, from the first law, says things want to go straight.
Precisely. So if something's moving in a curve, not a straight line, there must be some force constantly pulling it off that straight path. For circular motion, that means a force constantly pulling inward, toward the center. a centripetal force.
Ah, centripetal, not centrifugal, pulling in, not pushing out.
Right. And Newton interpreted this continuous inward pull as a kind of continuous motive force. You could almost think of it like an infinite series of tiny, instantaneous impacts, each one nudging the object's momentum slightly towards the center, keeping it on the curved path.
Instead of one big whack, it's like constant little taps.
Sort of, yeah. This idea of force acting continuously to change the direction of motion was absolutely key for understanding things like orbits.
And he formalized a lot of this in the Principia, starting with some really fundamental definitions. Which ones do the sources flag as most important?
Okay, first, quantity of matter, which is basically what we now call mass. He saw it as this intrinsic property, defined it as density times volume, but crucially, he found he could measure it using weight. He even did these incredibly precise pendulum experiments, confirming that mass was directly proportional to weight, at least in one location.
And that link between mass as inertia and mass as gravitational weight.
Yeah, the sources point out he noted they seem to be the same property. The thing resisting acceleration was also the thing involved in gravity. But he didn't have a theory for why they were equivalent. That's the equivalence principle, which just kind of sits there in his system as an observed fact.
Interesting. What else did he define?
Quantity of motion, defined simply as mass times velocity are modern momentum. This is the thing that force changes. And he talked about three kinds of force. There was innate force, or vis insita, sometimes called vis inertia, which is just the body's inherent tendency to resist changes in motion, basically inertia itself.
Okay.
Then impressed force, which is the external push or pull that causes a change in motion. That's the force in the second law.
Got it.
And finally, centripetal force, the one we just discussed, the force that continuously pulls things toward a center, like in orbits.
So with those definitions locked down, he states the laws. How do the sources present his actual wording?
Law 1, everybody perseveres in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed.
Law 2. A change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed.
Law 3. To every action, there is always an equal and opposite reaction. In other words, the actions of two bodies upon each other are always equal and always opposite in direction.
They seem so, I don't know, almost self-evident now, but applying them universally led to his perhaps most famous discovery, universal gravitation. How did he piece that together, according to these accounts?
It was a brilliant synthesis of several ideas. First, he connected that concept of centripetal force needed for orbits with Kepler's mathematical laws describing how planets actually orbit. He figured out that the force pulling planets toward the sun must decrease with the square of the distance and inverse square law.
Okay, the math pointed that way.
Then came the legendary comparison. He calculated the acceleration needed to keep the moon in its orbit around Earth and compared it to the acceleration of a falling object like an apple right here on Earth's surface. And accounting for the moon's much greater distance, he found they matched. The force pulling the moon was the same kind of force pulling the apple, obeying the same inverse square law. Terrestrial and celestial physics were unified by a single force: gravity.
Wow. But the sources say the really huge philosophical jump wasn't just unifying them, but the nature of this force.
Exactly. Gravity, as Newton described it, acted without a medium. Action at a distance.
And that was so radical because
the prevailing mechanical philosophy, especially from Descartes, insisted everything had to happen through direct contact. Pushes and pulls transmitted through some intervening substance, like invisible gears or fluids filling space. The idea of one body reaching across empty space to pull another instantly, that sounded like magic, like something occult.
But Newton just accepted it.
He famously said he didn't know the cause of gravity, why it worked that way. But the mathematical law describing how it worked was undeniable, derived from observations. It acted instantaneously across the void, and that was that. It was a major break for mechanism.
And mass quantity of matter plays that dual role again here, right?
Absolutely crucial. The sources stress this point. The very same property, mass, determines both a body's inertia, its resistance to being accelerated, and its gravitational charge, you might say. Both how strongly it pulls other things gravitationally and how strongly it feels the pull from others.
And again, he noted this equivalence, but didn't explain why inertial and gravitational mass are the same.
Right. It remained an empirical observation, a deep puzzle embedded within his own hugely successful theory.
A puzzle hinting at deeper connections, maybe?
Perhaps. And this gravitational force wasn't just local, it was universal. Every particle of matter in the entire cosmos attracts every other particle according to this inverse square law.
Mhm.
This is the picture. A universe governed by a single, quantifiable universal force acting mysteriously across space. A total rethink.
Now, moving beyond the purely technical parts, the sources talk about these sections in the Principia called the Scholium. What exactly were those?
A scholium is basically an explanatory note, a commentary. But in the Principia, they're more than just footnotes. They're places where Newton pauses the relentless mathematical proofs to offer broader context, clarify his underlying assumptions, and sometimes even explore his philosophical and, yes, theological perspectives.
So they're windows into his thinking beyond the equations, connecting the math to the bigger picture.
Exactly that. The sources highlight two main ones: the preliminary scholium in Book 1, right after the definitions and laws, and the general scholium added much later at the very end. They're absolutely essential for understanding Newton's worldview and how he saw his physics fitting into, well, everything.
Let's dive into that first one then, the preliminary scholium, because that's where he tackles this massive philosophical debate, absolute versus relative.
Yes, this is where Newton really draws a line in the sand. He argues forcefully for the existence of absolute time, a true mathematical time that flows uniformly by its very nature, completely independent of anything external, like clocks or planetary motions. It's the underlying universal duration.
Distinct from the time we actually measure.
Right. That measured time he calls relative time. It's just the sensible, everyday measure we get from observing motion, the swing of a pendulum, the rotation of the Earth. It's an approximation, a proxy for the real, absolute flow.
And he does the same for space.
Exactly the same logic. He posits absolute space, a true mathematical space that exists in and of itself, independent of any objects within it. It's infinite, immovable, the fixed stage for everything. This is distinct from relative space, which is the space we perceive defined by the positions of objects relative to each other, like the space inside this room defined by the walls.
So relative space is just how we measure bits of the true absolute space.
Pretty much. And place, for Newton, is just a specific part of absolute space that a body occupies.
Okay, this feels incredibly abstract. Why did Newton feel the need to invent these unobservable absolutes? Why does this philosophical question, is motion absolute or just relative? Why does it even matter for doing physics?
Ah, that's the critical point. It matters fundamentally to what motion is. If motion is purely relative, then saying something is moving just means its position is changing relative to some other chosen object. It doesn't have motion as an intrinsic property of itself.
Okay.
And if that's the case, motion becomes sort of slippery. Is anything really moving, or is it just a matter of perspective? Whose reference frame is the right one?
Right.
Does motion lose its objective reality? It becomes just a description of relations.
So if everything's just relative, there's no such thing as true motion.
That's the problem Newton saw for his physics. If, however, absolute motion exists motion relative to absolute space, then a body can possess motion or rest as an intrinsic state, regardless of what other visible objects are doing. Motion becomes a real objective feature of that body.
But that requires...
It requires a fixed backdrop, an ultimate reference frame, like absolute space, against which this true objective motion can be defined and measured. The sources really emphasize that this debate isn't just semantics. It fundamentally shapes your concept of physical reality and the very nature of the laws governing it.
To really get this debate, we probably need to step back. The sources trace this back to Aristotle, right?
Right. Aristotle's view dominated for centuries, and it was very different. He believed the cosmos was completely full, no void, no empty space, a plenum.
No empty space at all?
None. And because there was no empty container, place wasn't an absolute coordinate system. Your place was defined as the innermost motionless boundary of whatever was surrounding you.
So my place is the inner surface of the air touching me.
Essentially, yes. And since there was nothing outside the outermost sphere of stars, there was literally no space beyond that. This naturally led to a relative view of motion. Motion was changing your surroundings, changing place relative to other bodies.
But the sources mention a wrinkle in Aristotle, something that hinted at, maybe, not purely relative.
Yes, this is a really interesting nuance. Despite rejecting absolute space, Aristotle had this idea of natural motion. Heavy things, like rocks, naturally strove downwards toward the center of the Earth, which he considered the fixed, absolute center of the whole universe. Light things, like fire, strove upwards.
So that motion wasn't just relative to the air around it.
No, it was directed towards a specific point in the cosmos, determined by the inherent nature of the object and the structure of the universe itself. It wasn't defined by convention or relative to just any old container.
So even without absolute space, there was a kind of privileged direction, a cosmic center.
Exactly. It suggests an implicit sense of absolute orientation or perhaps even absolute motion, defined by the universe's inherent structure, not just by relations between objects. This maybe laid some groundwork for later thinkers to question pure relationism.
Okay, so how did we get from Aristotle's full Earth-centered cosmos to the mechanical picture Newton was working with? The sources point to two huge shifts.
First, obviously, the Copernican revolution, taking the Earth out of the center and making it just another planet moving around the sun. That changed everything.
How so regarding motion?
Well, if the Earth itself is moving, then defining motion simply relative to the Earth suddenly becomes problematic. It immediately forces the question. Motion relative to what? The sun? The distant stars? Something else entirely? It cracked open the whole concept of a single, obvious reference frame.
Okay, that makes sense. And the second big shift.
The revival of atomism, the ancient idea pushed by people like Gassendi that matter is ultimately composed of tiny, indivisible particles moving through genuinely empty space. A vacuum came roaring back.
Directly contradicting Aristotle's filled universe.
Completely. This required accepting empty space as real, as a sort of container in which atoms moved. Aristotle had denied the possibility of a void.
And these two things, a moving Earth and particles in a void, paved the way for the mechanical worldview.
Yes. The picture emerged of a universe made of tiny bits of matter moving according to mechanical laws in a vast emptiness. This was the backdrop Newton inherited.
And Descartes was a key figure here, but he took a different path regarding space and motion. He doubled down on relationism.
He did, in a very specific way. For Descartes, the absolute essence of matter was extension, just having size and shape. Since space is also defined by extension, he concluded that matter is space. They are identical.
So no empty space possible for Descartes either.
Correct. The universe had to be a plenum, completely filled with matter, perhaps of different kinds, but no vacuum, which meant motion couldn't be defined as moving through empty space.
So how did he define motion then?
Purely relatively. A body moves when it changes its position relative to the bodies immediately surrounding it, its contiguous neighbors.
Just the things touching it.
Yes. But he introduced a distinction. He talked about proper motion, which was the specific transfer of a body from the vicinity of one set of neighbors to the vicinity of a different set. He argued this proper motion was unique for any body at any instant, unlike arbitrary relative motion you could define with respect to distant objects.
So even though he rejected absolute space, he tried to salvage a kind of special, physically real motion.
Exactly. The sources point out that his laws of collision, his physics, actually depended on this concept of proper motion. So while denying absolute space, he still needed a privileged, physically significant notion of true motion for his system to work.
Which sets the stage for Newton's strong rejection of all this. He insisted on absolute motion.
He absolutely did. The sources show he explicitly argued against this Cartesian relationism. He felt it was inadequate for explaining the dynamics he was developing, especially involving acceleration and rotation. For Newton, true motion, real motion, had to be defined relative to something unchanging and absolute, that absolute space he postulated. And likewise for absolute time. This absolute framework was the necessary foundation for his laws.
But arguing for something you can't actually see or touch, like absolute space, that's tough. How did he try to provide evidence? This is where the famous thought experiments come in, right?
Precisely. He couldn't point to a spot in absolute space and say, there it is. Instead, he pointed to the observable effects of certain kinds of motion, specifically rotation or acceleration, effects that seemed independent of relative motion to other bodies.
Like a spinning bucket argument.
That's the classic one. Imagine hanging a bucket full of water from a rope, twisting the rope up tight, and then letting it go.
Okay, what happens?
Initially, the bucket starts spinning rapidly, but the water inside lags behind due to inertia. The water surface stays flat. At this point, there's maximum relative motion between the spinning bucket and the still water.
Right.
Then friction gradually drags the water along, and it starts spinning with the bucket. As the water spins faster, its surface becomes concave. It climbs up the sides of the bucket. Eventually, the water and bucket might spin together with no relative motion between them, but the water surface is deeply curved.
And even if the bucket stops, the water keeps spinning and stays concave for a bit.
Exactly. Newton's killer point was this. The concavity, which is a real physical effect caused by centrifugal forces, doesn't correlate with the relative motion between the water and the bucket. The surface is flat when relative motion is high, and curved when relative motion might be zero when they spin together.
So the curvature must be due to something else.
It must be due to the water's rotation relative to something absolute. The concavity is empirical evidence, Newton argued, of the water's absolute rotation. Its rotation with respect to absolute space itself. It challenges the idea that only relative motion matters.
So the physical effect proves the absolute motion, which implies the existence of absolute space as the necessary reference frame.
That was his argument, a very clever way to try and make the unobservable observable through its effects.
He had another one too, the two globes thought experiment.
Similar logic. Imagine two identical spheres connected by a cord floating completely alone in an otherwise empty infinite space. No other reference points exist.
Okay, isolated system.
Now, if these two globes are rotating around their common center of mass, the cord connecting them will become taut due to the centrifugal forces trying to make them fly apart.
And the tension in the cord is the key.
Yes, that tension is a real, measurable physical effect. It indicates that the system is truly rotating. But since there's nothing else in the universe for them to be rotating relative to, Newton argued their rotation must be absolute relative to absolute space itself.
So again, an observable internal effect, tension, points to an absolute state of motion independent of external relations.
Exactly. For Newton, these weren't just philosophical musings. They were arguments from physical phenomena designed to provide empirical grounding for the necessity of absolute space and time in his dynamical system, where forces cause absolute accelerations.
Okay. Beyond these deep concepts of space, time, and motion, Newton also laid out his approach to scientific thinking in his rules of reasoning. What did the sources tell us about these?
These 4 rules, which he added to Book 3 of the Principia later, are really insightful. They show his methodology, this careful balance between empirical observation grounding everything in what we see and rational principles for drawing conclusions. They were his guideposts for doing natural philosophy.
Rule I sounds like Occam's razor. Economy of causes.
Pretty much. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Basically, keep it simple and stick to causes that are actually needed to explain the data. Don't invent elaborate, speculative explanations if a simpler one works and is supported by evidence, both empirical, explaining appearances, and rational, sufficiency truth.
Okay. Rule 2, uniformity of nature.
To the same natural effects we must, as far as possible, assign the same causes. This is a huge foundational assumption for all of science, really. It's the belief that nature is consistent. The same laws apply here as they do on Jupiter. The same laws applied yesterday as will apply tomorrow.
And this justified applying gravity universally.
Absolutely. It allowed him to say the force making the apple fall is the same kind of force holding the moon in orbit. It's a rationalist assumption about cosmic order, but one that his work showed had incredible empirical success.
Makes sense. Rule 3 is about generalizing qualities.
Yeah. The qualities of bodies, which are found to belong to all bodies within experiments, are to be esteemed the universal qualities of all bodies whatsoever. This is about cautious generalization. If every object we can test has mass or inertia or is extended in space, then we're justified in assuming all matter has these properties, unless or until we find evidence otherwise.
So, grounding universal claims in experiments, but acknowledging it's an assumption.
Right. It's empirical generalization combined with a kind of realism about properties, rejecting unknowable hidden essences.
And Rule 4, this sounds important induction and provisional truth.
Extremely important. Propositions gathered from phenomena by induction should be considered either exactly or very nearly true, notwithstanding any contrary hypotheses, until yet other phenomena make such propositions either more exact or liable to exceptions. This is Newton acknowledging the inductive nature of science.
Meaning conclusions drawn from specific observations are held as true.
Provisionally. They are our best understanding based on current evidence, but they are always open to revision, refinement, or even rejection if new observations or experiments come along that contradict them or require modification. The sources note this really anticipates later ideas about scientific fallibility and the need for potential falsification. Science progresses.
Okay. And finally, the general scholium, added at the end. The sources suggest this is where he really connects his physics to his broader worldview, including theology.
Yes, this is a fascinating section. It goes way beyond the mechanics. One of the most famous statements is here. Hypotheses non fingo. I frame no hypotheses. Or, perhaps better, I feign no hypotheses.
Meaning?
He was specifically addressing the cause of gravity. He was saying, look, my law of gravity is derived directly from observations from phenomena. It describes how bodies attract. But why they attract, what the underlying mechanism is, I don't know, and I'm not going to invent some speculative, unproven story about it, unlike, say, the Cartesians with their vortices.
Stick to what the evidence tells you.
Exactly. But then he pivots. He argues that the incredible order, harmony, and mathematical precision revealed by his laws couldn't possibly arise by chance. It points unmistakably, he argued, to an intelligent, powerful, eternal creator.
So the clockwork implies a clockmaker.
Essentially, yes.
Yeah.
He saw the universe governed by an intelligent and powerful being whose existence and attributes were manifest in the design and regularity of nature.
And he connected his ideas of absolute space and time back to God here, too.
He did, in a really profound way. He refers to space as God's sensorium, almost like the divine consciousness or presence. The infinite, eternal, unchanging nature of absolute space and time were, for Newton, reflections of God's own omnipresence and eternity. The very order embedded in the laws was a testament to God's power and dominion over the universe.
Wow. Okay, so pulling all these threads together now, the laws, the definitions, the absolutes, action at a distance, gravity, the methodology, the theology. What's the summary picture? What did the Newtonian world look like based on these sources?
It's a universe fundamentally composed of discrete particles, or corpuscles, tiny bits of matter moving and interacting. All the phenomena we see at the macroscopic level were ultimately to be explained by the motion and interactions of these underlying particles. Though the sources note, he didn't really specify what kinds of fundamental particles there were.
And the key unification.
The complete abolition of that old split between earth and heavens. The same laws of motion, law of gravity, applied universally to all bodies everywhere. Representationally, all bodies have mass, etc. And dynamically, all obey ESMA, gravity.
All playing out on that absolute stage.
Yes, against the backdrop of absolute space and absolute time. These were real, existing independently of matter, providing the fixed, unchanging framework necessary for defining true motion and for the laws themselves to operate universally. Part physical necessity, part metaphysical or even theological construct.
And interactions were mediated by forces.
Forces were the agents of change. Particles interacted through forces, crucially including gravity acting instantaneously at a distance across empty space, a concept that remained philosophically tricky but worked mathematically. Forces determined how the momentum of bodies changed over time.
And that still puzzling dual concept of mass.
Right. The sources reiterate this. Mass appears in two ways: as inertial mass, resistance to acceleration in ESMA, and as gravitational mass, the charge that creates in response to gravity. Newton took their observed equivalence as a brute fact, a fundamental property of nature, without a deeper explanation for why they were the same.
And the engine driving it all was the second law.
FA, or force equals rate of change in momentum, was the core operational principle connecting force, mass, and acceleration. It allowed for prediction and calculation. Although, as the sources do point out, even within this incredibly successful framework, the fundamental concepts themselves, force, mass, acceleration, carried certain conceptual ambiguities and challenges when you tried to define them with ultimate precision. Their practical utility was immense, but foundational questions lingered.
This whole Newtonian picture was just staggeringly successful for centuries, but the sources end by looking ahead, briefly touching on its eventual breakdown.
Yeah, it's quite the dramatic ending note. The sources essentially say that the core concepts of the Newtonian worldview, universal laws, particles, absolute space and time, action at a distance forces underwent such radical transformation in the 20th century that arguably none of them remain intact in our current best theories, like relativity and quantum mechanics.
Wow, none. How did such a successful picture unravel so completely?
Well, several things happened. The idea of truly universal laws fractured. We now have general relativity describing gravity and the large-scale structure of the universe, and quantum theory describing the subatomic realm, and they famously don't quite fit together yet. No single unified picture.
And the particles and forces.
The focus shifted dramatically from particles interacting directly, even at a distance, to fields being fundamental. Things like the electromagnetic field or the gravitational field in GR. Particles are more like excitations of these fields, and interactions happen locally through the fields, replacing Newton's instantaneous action at a distance.
And that absolute stage, space and time, what happened there?
That underwent perhaps the most mind-bending change. Newton's absolute, unchanging, passive background was overthrown by Einstein's general relativity. Space-time isn't a fixed stage. It's a dynamic physical entity itself. It's curved by mass and energy, and its curvature is gravity. Objects just follow the straightest possible paths, geodesics, through this curved spacetime.
So gravity isn't a force in space anymore, it's the sheep of space-time.
It's exactly a complete reconceptualization.
And the whole mechanical billiard ball view of the world.
That also dissolved, especially with quantum mechanics. QM describes the world not with definite particle positions and velocities, but with abstract mathematical objects, state vectors, wave functions that encode probabilities. The fundamental reality seems non-local, probabilistic, and definitely not just tiny things bumping into each other in the classical sense. Change happens through the evolution of these abstract states.
And as you hinted, maybe some seeds of this were already there in the conceptual ambiguities within Newton's own system.
The sources suggest so. The difficulty in perfectly defining force or mass, the mystery of the equivalence principle, the philosophical discomfort with action at a distance, these internal tensions and unanswered questions perhaps pointed towards the need for the deeper, stranger frameworks that eventually replaced the Newtonian picture.
Okay, let's take a breath after that whirlwind tour through Newton's universe and its eventual transformation.
It really drives home that Newton wasn't just a brilliant calculator. He was grappling with the absolute deepest philosophical questions about reality, time, space, and causation. And his answers shaped science for centuries.
And his insistence on absolutes, backed by things like the bucket argument, even if ultimately superseded, was clearly what he felt was necessary to make his dynamics work. It provided that solid ground conceptually.
Absolutely. And those rules of reasoning, they still feel incredibly relevant today, don't they? That blend of empirical grounding, logical rigor, demand for simplicity, and yet acknowledging that scientific truth is provisional.
So, pulling back, what's the big takeaway for you listening to this? I think it shows powerfully how intertwined physics and philosophy really are. The foundational assumptions of any physical theory rest on deep ideas about what kind of reality we live in.
And it's a great reminder that even the most established, most successful scientific frameworks like Newton's incredible clockwork universe contain within them the potential for future evolutions, often hinted at by those subtle conceptual puzzles or unanswered philosophical questions.
Right. And here's where it gets really provocative, I think. Consider how those fundamental questions Newton wrestled with. What is motion, really? Is space just relationships, or is it a thing in itself? How do things influence each other across distances? These exact same kinds of questions, maybe phrased differently, are still driving physics today. Think about quantum entanglement, the nature of space-time at the Planck scale, the search for quantum gravity.
It's true. The questions endure, even as the answers become stranger and more complex. What does that tell us about the enduring power of fundamental philosophical inquiry to push the boundaries of science, generation after generation? Something to ponder.